Hello friends, good morning. Today we talk on the topic training neural networks. We have neural networks in deep learning which is millions of nodes, the hidden nodes, millions of hidden nodes, and there are a number of edges is quite more than that, and each edge weightage is a parameter. So how do we tweak these millions of parameters to get our optimized output? Neural networks can be used without knowing precisely how training works, just as one can operate a flashlight without knowing how the electronics inside it work. Most modern machine learning libraries have greatly automated the training processes. Owing to these things and the topic being more mathematically rigorous, one may be tempted to set it aside and rush to the applications on the neural networks. So how we apply the mathematics while training a neural network is quite important. Why it is hard? Why this topic is so hard? Why the training is so hard? If we consider a deep learning network where on the left we have the input nodes, on the right we have the output nodes, and there are millions of hidden nodes. Just one edge from the output node influences so many edges in the next layers. That is why it becomes so intractable to estimate the weights of the edges separately. So we use gradient descent method. If we talk about linear and logistic regressions, those are also neural networks. The output is given by sigma of b, the bias b plus w1x1 plus w2x2 etc. up to wn(xn), where w1, w2, wn are age weights and x1, x2, xn are input. The bias can be set to 0 also. For linear regression, sigma x equal to x. We have the linear regressor b plus w1 x1 plus w2 x2 plus wn xn. Whereas for logistic regression, we have sigma x to be a sigmoid function 1 by 1 plus e to the power minus x, which always lies between 0 and 1. So linear and logistic regression could also be seen as a part of neural networks. There is a concept of cost function, which is a parameter of the actual values, the predicted values, and the parameter set w. So while training a neural network, we need to minimize the cost function over the parameter space w. We considered the values of y, and y had to be constant, and then we minimize the loss to find the values of w. So that is the general idea behind neural network training. Gradient descent method, we consider the loss function j, or where j is the Jacobian. So gradient of we calculate the gradient of j at w, del j del w1, del j del w2, dot 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 del j del wn, and iteratively starting from a solution of w, we use the old solution in w minus alpha jw, where alpha is a small learning rate, and we get the new value of w, and then again we use it in the same equation. So this is the iteration process in gradient descent method that helps us in finding the minimums. Now in general, in neural network, the loss function is not well behaved. There are so many local minimums and maximums, but this is not a problem. It turns out that this is not a major problem in deep learning, because when there are enough hidden units alongside some other criteria, most local minimum are good enough, being reasonably close to the absolute minimum. So this is not really a practical problem, the local minimums. But considering the performance of the gradient descent method we go for stochastic gradient descent, which says that in stochastic gradient descent we shuffle our dataset and then go through each sample individually, calculating the gradient with respect to the single point and performing a weight update for each. So that is called stochastic gradient descent. SGT helps us get the local minima and the saddle points by making updates more jerky and erratic, which can be enough to get unstuck if we find ourselves in the bottom of a valley. If we consider the concept of momentum, this is the gradient descent method, Wt equal to Wt minus 1 alpha j at Wt minus 1. So we use the old values to get the new values and repeat the process iteratively till it converges. But in momentum, we define new variable zt, which is beta zt minus 1 minus gradient at jwt minus 1. And we get the new value of weights, Wt, using the value at Wt minus 1 in minus alpha zt. So we are not directly using the gradient vector here. Rather, we are using a beta zt minus 1 plus the gradient at t minus 1. So this is the momentum method. In the parameter update, we have replaced the gradient jwt with a more complex function zt that takes into account the gradient in the past time steps. It helps us to go backwards and bring up the past values. Adaptive methods. The ith weight, the new value is old value minus alpha by root over gi plus epsilon del j del wy, where gi root over gi plus epsilon represents the sum of squares of the gradient for the parameter for each step since training began. Now we go from linear regression to ridge regression by tweaking a function of the weights so that more is the weight, more is the penalty. So here we do similar thing. Considering the squared error loss function, we update the loss function with a regularization factor Rf, which is lambda times summation wi square. The effect of this regularization term is that it helps gradient descent find a parameterization which does not accumulate large weights and have such wild swing as we saw above. Dropout is an interesting concept. Dropout is a clever technique for regularization which was introduced by Nitish Srivastava et al. In 2014. During training, when dropout is applied to a layer, some percentages of its neuron, a hyperparameter with common value being between 20% and 50%, are randomly deactivated or dropped out along with their connections. Which neurons are dropped out or constantly shuffled randomly during the training? The effect of this is to reduce the network's tendency to over-depend on some neurons since it can't rely on them being available all the time. Finally comes the concept of backpropagation. The basic idea is that backpropagation makes it possible to compute all the elements of the gradient in a single forward and backward pass through the network rather than having to do one forward pass for every single parameter as we would have to using the naive approach. This is enabled by utilizing the chain rule in calculus, which lets us decompose a derivative as a product of the individual functional parts. So backpropagation, we go backward and forward till we reach a stable solution. I'll stop here. The entire talk is based on the article How Neural Networks Are Trained. Please like, comment, share and subscribe my video. I am available for one-to-one sessions too. Thank you.